Altera makes a variety of FPGAs, from the low complexity Flex and Cyclone parts to the more power-hungry beasts of their Area and Stratix lines. They also have a variety of different CPLDs, from the older MAX 7000 and 3000 to the newer MAX 2 and MAX 5 parts. The difference between these entry-level and professional-grade CPLDs and FPGAs is the size of the part measured by the number of macro cells or logic elements that can be used, as well as the different types of hardware peripherals they contain, like DSP modules, DCM clock modules, RAM modules, and more. To make things simpler for this course, we've opted to use an entry-level PLD, the EPM 3032, on a breakout board so that we have access to all of the pins and so that we can easily plug it into a breadboard and start prototyping. As with any new part, you should first look at the datasheet to see what it is really about. MAX 3000 type devices are all described in this device family datasheet. The important things that we want to highlight are that these devices are limited on how fast they can run. They are capable of 5 volt, 3.3 volt, and 2.5 volt digital logic, and these PLDs can vary in size from 44 pins to 256 pins. Here's the overview of the EPM 3032 part that we'll be using. You can see that it has a maximum of 600 digital logic gates, 32 macro cells, and 34 input or output pins. 34 GPIO pins might seem like a lot, but one thing you'll find out as you continue studying is that you can never have enough I/O pins. The other section of this datasheet that we wanted to highlight is the device pinout. Here you can see the pinout for both the PLCC and TQFP type packages. We'll be using the TQFP type package. On this pinout, you can easily see and identify the VCC power, GND ground, general purpose input and output, JTAG interface, and the special input pins like global clocks and global clear. Each of the pins labeled I/O can be configured as an input or as an output, and its type of 5 volt, 3.3 volt, or 2.5 volt logic defined. The design flow for FPGA and CPLD follows a common pattern every time you start a new design. First, you choose the part that you will use and enter in your core design with either a hardware description language or schematic entry. Then your design will be synthesized to check for syntax errors and to create a netlist for use in the next phase. The design implementation consists of translating the netlist, mapping it, and finally placing and routing it on the silicon fabric of your FPGA or CPLD. Afterwards, you're ready to generate the programming file and then actually program the part. The final phase is testing to make sure everything is working. This might involve using a signal analyzer like SignalTap, modifying and recompiling your code, or you could just be one of those lucky people whose code works perfectly the first time. But before we can follow this design flow, we're going to need to get the Altera tools to go with our EPM 3032 CPLD. To do that, go to Altera's website at altera.com. Under Design Tools, go to Design Software. Next we want to get the Quartus 2 Web Edition, so click the Download Software Web Edition Free button. Choose the version 13.0 Service Pack 1, as well as the operating system you're using. I have Windows 7. Also, I'll choose to use the direct download. Then click Combined Files and the Download button. Altera will ask you for account information. There's no cost to create an account, so don't worry. After logging in, it will redirect you to the download page and start the download. The complete file is 4.4 gigabytes and includes a lot of material that you might not need. But one day, you might be curious to experiment with other features, so I'd say download it all. And after the download is finished, use a program like 7-Zip or WinRAR to extract the installer. Then go ahead and run the setup batch file to begin the install process. The install process is just like any other program. You click next a few times, agree to sign your life away, and then it takes 5 to 10 minutes to load everything onto your computer. Now click Finish and then open up the newly installed Quartus 2 program. Here we can finally begin the first part of the design process, Design Entry. To do that, go to File, New Project Wizard. This opens up the Project Creation Wizard that asks you some questions in order to set up initial project properties. First, we set up the folder location where we want to save the project. I'll put mine on the desktop in a folder called FPGA Lesson 2. Next, the name of the project will be Lesson 2. This project name is important because it must be used as the top level in your code. We'll see this in a few moments. Next, we'll choose the device that we're using, a MAX 3000A series TQFP 44-pin CPLD. And now our project is set up. The entity box here shows the hierarchy of modules. The top module for this project right now is called Lesson 2. Down here are the synthesize, translate, map, route, and programming file generation tools. And at the moment, we don't have any files in the project, so let's add one. Go to File, New, and choose VHDL File. This will add a new VHDL file to our project. Throughout this course, we will use VHDL as our design entry hardware description language. It is not our intention to teach this language in this course, but to use it in simple ways to build different digital logic elements. If you are ever curious to learn more details about the VHDL language, there are numerous free resources online that you can refer to. So now, let's write some code. The first thing you will commonly see in VHDL files is the header library IEEE and use IEEE standard logic 1164.all statements. These are similar to header statements in Java or C. They are telling the synthesizer to use IEEE's standard logic libraries. Next, we create the top-level entity. This top-level entity is like the doors around a building. It defines how many inputs and outputs the module has. We define our Lesson 2 entity as a port with one standard logic type output called LED0, and we close the entity with an end Lesson 2 statement. To add comments in VHDL, you simply press the minus key twice, as we've done here, to show that pin 22 should connect to LED0. Now we need to create the architecture. If the entity is like the doors around a building defining inputs and outputs, the architecture would be what's inside the building, how it is structured. We'll call our architecture RTL for the Lesson 2 entity. And our architecture will simply tell LED0 to be a digital logic 1. Then we end the RTL architecture statement. Go ahead and save the file as lesson2.vhd and double-click the Compile Design button. Quartus takes you to a design summary window and it will start synthesizing and implementing the design. After a moment, it completes successfully and the flow summary shows you how much space is used and how many pins are required for the design. Additionally, there are many log files that tell you how the compilation process went, but we won't go over those now. Next, we need to map the design we entered to the physical part we're using. Go to Assignments, Pin Planner, and here you will see all the pins on the device and that the tool automatically chose a location for LED0 at pin 42. This is the wrong location, so double-click the location area for LED0 and type in pin underscore 22. Then close the window and recompile the design. This time, LED0 is located at the correct pin, so our design is all set and ready. So now, let's switch gears and take a look at the schematic. The hardware schematic starts with the power regulator circuit for the CPLD, which downregulates 9 volts to 3.3 volts. So first, we use a 9-volt battery connecting to an LM317 voltage regulator. One 10 microfarad capacitor is connected to the voltage input, and then we have two resistors, 240 ohm and 390 ohm, that form a voltage divider to set the LM317's output to 3.3 volts. Another 10 microfarad capacitor is placed on the output 3.3 volts from the LM317. And finally, we use a resistor and an LED as a power good notification. Next, we have the CPLD connections. The 3.3 volt power connects to pins 9, 17, 29, and 41. The ground connects to pins 4, 11, 16, 24, 30, and 36. Our infamous LED0 comes out of pin 22 to a 470 ohm resistor and LED. Finally, these 4 lines are the JTAG lines which connect to the JTAG port on the breakout board. And that's the schematic. If all goes correctly, we should be able to turn on that LED. To start the experiment, first we'll go through all the parts necessary to build up the circuit. The larger parts are a jumper wire kit, components kit, and a breadboard. The specific parts from the components kit are the CPLD breakout board, LM317, two 10 microfarad capacitors, two 470 ohm resistors, a 390 ohm resistor, a 240 ohm resistor, two red LEDs, and a 9-volt battery connector. To build the circuit, first we need the breadboard. We'll use two orange jumper wires to connect the power and ground bus lines together, and then connect the 9-volt battery connector to the breadboard. Next, we'll build the power regulation circuit, which starts with connecting the LM317's V-in pin 1 to the 9-volt battery connector's red wire. The 240 ohm resistor connects to V-out pin 2 and adjust pin 3 of the LM317. The 390 ohm resistor connects to the adjust pin 3 of the LM317. Then a wire connects the V-out pin 2 of the LM317 to the power bus, and another wire connects the 390 ohm resistor to the ground bus. Then we add the 10 microfarad capacitor from the 9-volt battery power to ground, and another 10 microfarad capacitor connects the power bus 3.3 volts to ground. Finally, we add a 470 ohm resistor from the 3.3 volt power bus to an LED that connects to ground, completing the voltage regulation circuit. Next, place the CPLD breakout board at the opposite side of the board. We'll use yellow wires to connect all of the VCC pins to the red power bus. Then we'll use dark green wires to connect all of the GND ground connections to the ground bus. And finally, a 470 ohm resistor connects from pin 22 to an LED that connects to ground. And now our circuit is ready. So get your JTAG programmer, 9-volt battery, and laptop with the Lesson 2 project ready to use. First we'll connect the 9-volt battery to the circuit to power it up. The power notification LED turns on. Then we'll connect the JTAG cable to the breakout board. The board has a small white mark that shows you which side the notch of the connector should face, so you don't put the connector on upside down. Now connect the JTAG programmer to your laptop. If this is your first time using the JTAG programmer, you should make sure that the driver is properly installed on your computer. You can do that by going into the Windows Device Manager and looking for the device, USB Blaster. Here you can see mine doesn't know which driver to use, so I'll tell it to look in the Quartus Drivers USB Blaster directory for a driver, and then let it install. Now you can see the Altera USB Blaster device shows up correctly. So let's go back to Quartus and double-click on the Program Device button. This will bring up the Programmer tool. In this tool, we first need to tell it what programmer we're using, so click the Hardware Setup button and select USB Blaster. Now you're ready. Sometimes the programming file generated by Quartus doesn't automatically show up in this window. If that happens, just click the Add File button, and in the lesson directory, go to the Output folder and click the .pof file. Now check the Program/Configure box, and finally start the programming process, and hooray! The LED turned on, just as we had hoped. To make sure we do indeed have full control of what's going on, let's try turning the LED off. To do this, we'll go back to our code and change the LED 0 to be a digital logic 0. Now recompile the design, reprogram the device, and this time the LED remains off, proving that the CPLD image is being loaded and that we can set a single output's logic level. The CPLD Hardware Hello World is admittedly more complex than in the microcontroller course, but that's because we're not simply loading software, we're configuring an entire hardware device, which takes more effort. As an example, the JTAG programming interface that we use can actually connect multiple CPLDs and FPGAs together in what is called a JTAG chain, so that each one can be configured individually, all while only using 4 electrical lines. This idea of chaining CPLDs and FPGAs together is quite helpful because then you only need to have one JTAG connector, but you can still access and reprogram many parts across a board or even multiple boards.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Now that we have Quartus installed and we know how to build a project, let's take it a step further and look at how to use a CPLD input to drive a CPLD output.